Hello and welcome to this video on the use of decision trees for classification. This is best illustrated with an example. So I'll use the very famous iris dataset to show how we select the most important features for classification. And that leads us into a discussion about entropy and information. Finally, we'll put all of these concepts together and construct a decision tree using Python. We all know what classification is at this stage, so let's dive right in. We'll begin with a discussion of the iris dataset. This dataset contains four input features and a target variable comprising three labels: sedosa, versicolor, and virginica, which are the three subspecies of irises. It's not a large dataset by any means, and it's perfect for illustration. If we were to look at a scatter plot of the data using just two of the input features, petal length on the y-axis and sepal length on the x-axis, we can clearly see three clusters corresponding to the three subspecies. Our goal is to fit a decision tree to this data. Now, if we want to construct an optimal decision boundary between the different classes, we need to decide which of the input features is the most important for classification. Is it sepal length or petal length? In other words, which feature can I use to obtain a split in the data that leads to more homogeneous leaf nodes? Ideally, if we can, we would like to obtain a split that results in each of the three classes belonging to three separate leaf nodes, which is anyways our goal for classification. We could begin with sepal length, for instance, and use a cutoff of 6 centimeters to start our decision tree. This does not appear to be an optimal choice because we end up with two highly impure child nodes. For sepal length values less than 6, we have a leaf node with data points corresponding to three classes. And on the other side, we have data corresponding to two classes. So the split is not informative enough and results in highly heterogeneous leaf nodes. Why should I worry about this for classification? For sepal length values larger than 6, for instance, the majority class is the label virginica, denoted by the purple data points. This implies that for any new data points that lies to the right of the split, I will classify the sample as a virginica sample, which as you can see is inaccurate, and I eventually end up with a high degree of misclassification. It's the same thing with the split on the right. So let's try again with a sepal length of approximately 7. We see that for values less than 7, we get a heterogeneous node containing all three classes. And for values larger than 7, we get a pure node, but the node only contains a subset of the virginica class. Now we could try other values, but we're always going to end up with a less than satisfactory split in the data. And we'll end up with impure or heterogeneous nodes. Well, what if we consider the other feature, which is petal length, and consider a split at 2.5 centimeters? This gives us a pure leaf on one side of the split and two other classes on the other side. While we didn't end up with a perfect split, this split is definitely more informative. We were able to separate out one of the classes entirely. In principle, this is the process for feature selection to start constructing a decision tree. We can also view this problem differently. By looking at the box plots of the data organized by subspecies, you can see that any choice of cutoff using sepal length inevitably leads to highly heterogeneous nodes, which essentially means that sepal length is not informative for classification, and at the very least, we should look at other input features. Using petal length shows us how we can create nodes that are relatively more homogeneous. In other words, we will begin our tree using petal length in our root node. So while these illustrations were enough to get an idea of the process, there is a formal approach to identifying the most important input feature. We know that sepal length leads to two impure child nodes, and impurity just means that there are many samples belonging to several classes, or rather, the child node is associated with quite a bit of heterogeneity or disorder. We want nodes that are homogeneous, and petal length led us to one such pure node. Disorder, as it turns out, can be quantified by the notion of entropy, just like in thermodynamics. A higher entropy is associated with more disorder. So, how do we get to entropy from what we were discussing? The formula for entropy is quite simple. It's the probability of each class times the logarithm of the probability summed up over each class. But what does this mean? Well, there's a negative sign. So using the definition of logarithms, we can rewrite the first equation to get the second equation. And this does not help us much either. So let's consider another example. Assume we have a bag with 100 balls, 99 of which are red and one is blue. The chance of picking up a red ball is 0.99. And if you were to randomly select balls from the bag, note their color, and put them back, you can be expected to get several red balls in a row, and you would think that the collection of balls is homogeneous. But if you did this enough number of times, you will eventually find a blue ball. Now, this event provides a wealth of information. Finding that one blue ball informs you that the bag is not homogeneous and that there is some disorder. The information content of that one rare event is huge. Now, this is not unique to this specific example. It extends to any rare event, say a tornado or a flood or engine failures. We simply learn more from rare events than a series of routine events. The information you get from picking up a red ball is small because a red ball is common. And notice that the inverse of the probability is also small. Picking up a blue ball, on the other hand, provides a wealth of information about the existence of heterogeneity or disorder in the bag, and notice that the inverse of the probability is large. It turns out that the inverse of the probability is related to the information content. Well, we do one more thing. We take the logarithm of the inverse of the probability. The logarithm is a monotonic function and does not affect the order of things. If you are wondering about the choice of base 2, that comes from information theory where we deal with 2 bits, 0 and 1, and we will not get into a discussion of information theory here. So to recap, finding a red ball provides us with very little information, while finding a blue ball gives us a lot of information. But here's the catch. While you do get a lot of information about the heterogeneity of the bag, when you pick up a blue ball, this event does not occur frequently. So the information that a blue ball provides is weighted by the probability of the occurrence of a blue ball, and the information that a red ball provides is weighted by the probability of occurrence of a red ball. And hence, we end up with the formula for entropy, which is the probability weighted average of the information content. So with that background, let's see how entropy varies with heterogeneity. So in this table, I examine different hypothetical datasets. One with a single class, which is homogeneous and has an entropy of 0. Then 2 classes of the same size, which has a higher entropy of 1. Then 3, 4, and 5 classes of the same size. And you can see that as we increase the heterogeneity, we also increase the entropy of the system. So why am I talking about all this? We should not forget we are discussing the concept of entropy in the context of decision trees. When we split a node, we want child nodes that are as pure as possible. We may have several choices to split a node. There may be several features or several values of a feature, and we want to choose an option that leads to nodes that are very homogeneous. If we choose a feature to make a split in the data that results in highly heterogeneous nodes, we potentially end up with a high rate of misclassification. We require low entropy nodes to avoid misclassification errors. The concept of entropy allows us to build decision trees that are parsimonious. That is, they have fewer splits in the data, but still lead to a low rate of misclassification. So now that we know where the concept of entropy comes into the picture, let's use this for our iris classification example. You can see that the entropy is the probability of each class multiplied by the logarithm of the inverse of the probability, giving us a value of 1.5 for the iris dataset. Let's see how we can use this information now. So let's assume we make a split in the dataset using a petal length value of 2.45. This gives us 2 child nodes, one of which is pure and the other which is a mixture of 2 classes. The entropy for the leaf on the left is 0, it's pure. For the one on the right, containing an equal number of data points belonging to 2 classes, the entropy is 1, and we get a total entropy of 1. Now let us plot this using a split on sepal length, for instance. In this case, we end up with two impure nodes containing a mixture of different classes. And here's the deal breaker. The total entropy ends up being 1.89, and this is worse than what we started off with. Remember, as we grow our decision trees, we want nodes that are more homogeneous than the parent node. In other words, the entropy should progressively decrease, and this is not happening with the use of sepal length. Hopefully, by now, you're completely convinced that sepal length is not an important feature for classification. And that's a lot of discussion, but what we are getting for free with the decision tree is also variable importance. The ability to distinguish between classes is improved with the use of petal length, and we should be spending more time, effort, and money collecting petal length measurements with greater fidelity if our goal is differentiating between the different subspecies of irises. So, with that background, we can now begin to construct our decision tree. We first start with our root node and the most important feature, and this leads us to two child nodes, one of which is a pure node and the other requires us to make a second decision. So with the remaining data points, we again consider a split using the most important feature at this stage, and it turns out that this is again petal length, and that leads us down the classifier to pure nodes or nearly pure nodes. So with this decision tree, we can also see this in action with a sepal length of 6.3 and a petal length of 4.7. And as you watch this video, you can see how we progressively move down the decision tree to classify our specific data point. So this is classification in action with a decision tree. Let us implement this in Python. So in this Jupyter notebook, we're going to be working on the same iris dataset. We're going to import all of our libraries and I do have the dataset contained in a specific CSV file. So you can again see that we have 150 data points. We're going to be selecting our input features. Our input features are sepal length, sepal width, petal length, and petal width. And the target variable is the label or the species. And in this specific output, you can see a matrix scatter plot of all of the four input features and the corresponding labels. You can see that there are three clusters corresponding to the three different facies. And our goal is to fit a decision tree to this data. We can also explore how each one of these species varies with respect to their sepal length measurements or their sepal width measurements or even their petal width and petal length. And you can see that again with these box plots, in general, the measurements associated with the petal length and petal width appear to be a little bit more discriminative between the different classes. And again, we can express that using the concept of entropy. So let's go ahead and begin our decision tree classification. We're going to be using a stratified split, and we're going to create a test data set of containing 20% of the data. And we're going to fit a decision tree classifier with all of the default options. And we'll just see how this does on fit this to the training dataset and see how well it does on the test dataset. So over here, I'm going to fit it to the test dataset and check and see what the accuracy is. Well, it turns out that the accuracy ends up being 93%. And remember that we're not going to be looking at accuracy alone. We're going to be looking at other metrics when we're dealing with classification. Specifically, when you're dealing with classification, you do want to look at the precision and recall, or at least take a look at the confusion matrix. because accuracy can be misleading when you have an infrequent number of classes. So we'll look at the confusion matrix and the classification report, and you can see that the precision and recall associated with the different species is relatively high, and so is the F1 score. But the size of the data set is relatively small. We only have 30 data points, 10 of serosa, 10 of versicolor, and 10 of virginica samples. We can also look at the confusion matrix associated with the test data set, and largely we can see that this is a diagonal matrix. There are some misclassified samples, but largely this is quite acceptable. Okay, in principle, we don't just do a train test split. Ideally, we do want to be identifying the optimal hyperparameters associated with the decision tree. Keep in mind that so far we've only used the default hyperparameters. So as we discussed with the regression problem, the hyperparameters of a decision tree that you want to control are going to control the level of splits in the data. It's going to control the degree of overfitting or underfitting. We have the first hyperparameter, which is max depth, and that controls how many levels of splits we're going to have in the tree. And largely, this would be the primary hyperparameter. We also have the minimum number of samples before you make a split. So this would allow us to essentially prevent the decision tree from overfitting the data by specifying a relatively large number. So if you specify a number to be 20, then any leaf that contains less than 20 samples is not going to be split further, and the tree terminates at that point. So this allows you to truncate the tree and prevent overfitting. And minimum number of samples per leaf also does a very similar task. It controls overfitting, and also specifies, also prevents the tree from becoming overly large and fitting each and every data point. We also have another feature which we're going to be talking about a little bit more when we talk about random forests. It's the maximum number of features that we're going to be using when we consider a split. So keep in mind that for this specific data set, we have 4 input features. There's sepal length, sepal width, petal length, and petal width. And in principle, at each split, we can consider all 4 features, or we can consider a random subset of the features. And this allows you to again come up with a very parsimonious decision tree. But largely, we are going to keep this out of the picture and discuss this in more detail when we discuss random forests. So, going back to our hyperparameter optimization, we're going to be using the following hyperparameters. We're going to be choosing maximum depth of 2, 6, and 8, minimum number of samples before you make a split of 10, 20, and 40, and we're going to be using 5-fold cross validation, and we're going to be scoring the models on the basis of accuracy. We're going to be fitting it to our entire data set, and let's see what we get. So that was quick because we only had to run 9 different models. We have 3 values for one hyperparameter and 3 values for another. 3 times 3 is 9, and 5-fold cross validation, so 9 times 5 is 45 different fits. Let's see which are the best models in this specific case. You can see that I have all of the 9 models over here, and the best model, there are several of them which are the best model. You can largely see that a max depth of 6 with a minimum number of samples per split of 10, that has a fairly high accuracy. It also has a relatively low standard deviation across each one of the splits. So remember, a decision tree is, we're using 5-fold cross validation, and we're fitting a model to the first split, and testing it against the first fold. That gives us some accuracy. Then in the second split, we're testing it against the second fold. We get another accuracy, and we don't want the accuracy to fluctuate a lot. We largely want the model to be insensitive to the choice of test data, and a low standard deviation in your test scores is indicative of something like that. So we're going to see which one is our best model. Largely, it's one of these four, and we're going to now just confirm that this indeed is the best estimator, in the sense that we want to apply this to the entire data set again and make sure that its performance across all of the five folds is pretty much the same. And so if you look at the accuracy obtained with five-fold cross validation using the best decision tree, you can see that the accuracy of each one of the five splits, five decision trees across the five folds, is pretty much the same. There's hardly any fluctuation between the different folds. And this is fantastic because we now have a decision tree that is fits the data very well and also generalizes to new data quite well. So this is the process by which we use decision trees for classification. And so just to recap, we began this video by talking about the concept of feature importance, and that led us to a discussion of entropy. And entropy essentially tells you which feature is likely to lead to more homogeneous nodes, nodes that allow you to classify new data points with a relatively low rate of misclassification. And with that background, we began to look at the application of a decision tree using the Scikit-Learn library, uh, and we applied it on the iris dataset, and eventually went through the whole process of hyperparameter optimization and came up with the best model that's suitable for this dataset. Thank you for listening.